The next lesson in our chemical bonding and nomenclature unit is on ionic bonding. We have two learning targets for this lesson, the first of which we want to be able to describe how an ionic bond forms. We have learned so far that when cations form, we say that the electrons are lost in order for that atom to become positively charged. So where do those lost electrons go? And then on the flip side, we know when anions are formed, they gain electrons. Where would those gained electrons come from? Well, if we consider this scenario, the most logical answer would be that electrons are transferred from one atom to another. In other words, electrons that are lost by one atom must be gained by another atom. And that is, in fact, what ionic bonding consists of. So let's take a look at an example. Let's consider the formation of a lithium ion and a fluoride ion. We know lithium has one valence electron. So here is a diagram to show this. Notice we're not showing all of the electrons in lithium. We write the symbol for lithium, Li, which notates its nucleus and any inner level electrons. And then we draw a dot next to it to show its one valence electron. These are referred to as dot diagrams or electron dot diagrams. Likewise, we know fluorine has 7 valence electrons. So for that, we'll draw the symbol for fluorine, which is F. Again, that denotes the nucleus and any inner level electrons. And then 7 dots around the outside to show its 7 valence electrons. So we know that lithium will want to lose its one valence electron to form an ion, and fluorine will want to gain one. This would complete the octet of both of those atoms. So that is exactly what happens. Lithium will lose its valence electron to fluorine. To show that on our diagram, we simply draw an arrow going from lithium's valence electron that it's losing over to fluorine to show that electron is being transferred. Well, because lithium has lost an electron and fluorine has gained an electron, this results in ion formation. So we could draw the results of that over here. Lithium lost one electron, so it now has a 1 plus charge, so Li plus. The fluorine gained an electron, so it now has a 1 minus charge, so F minus. These two ions are oppositely charged. And as we know, opposite charges will attract each other. So these two ions, the lithium ion and the fluoride ion, would be attracted to each other. That would result in an ionic bond. Because they are attracted to each other, they're going to be stuck together essentially. This leads us to our definition of what an ionic bond is. It is the electrostatic attraction of oppositely charged particles, or oppositely charged ions, as we would say here. Let's look at another example. We're told to draw a dot diagram to show how the compound sodium oxide forms. So sodium oxide, that would consist of sodium and oxygen. So we'd want to start by drawing diagrams similar to what we had before. Notice sodium has 1 valence electron. Oxygen has 6. Sodium wants to lose an electron to form an ion. Oxygen will need to gain. So sodium will give up its valence electron or transfer its valence electron to oxygen. And again, we show that by drawing an arrow going from the sodium's valence electron over to oxygen. But notice, oxygen is still short of its octet. Oxygen has 6 valence electrons to start with, so it needs to gain 2. So ask yourself, where is that second electron going to come from? If you said that electron is going to come from a second sodium atom, you would be correct. Oxygen still needs another electron, so we would need a second sodium atom to give it a second valence electron. So that second sodium atom will transfer its valence electron to oxygen. And this, like in the previous example, results in ion formation. So notice in this example, we have 2 sodium ions formed. Because we had 2 sodium atoms, each of them gave up its 1 valence electron. So we have 2 sodium ions, each with a 1 plus charge. And then we have 1 oxide ion with a 2 minus charge. And again, because these are oppositely charged, these ions will be attracted to each other, resulting in an ionic bond. Let's take a look a little more closely at the charges on those ions that we just saw in the last two examples. Here are the ions we formed in the first example with the lithium fluoride. Here are the ions that were formed in the second example. Take a moment and add up the charges on each set of ions. So what do we get if I add up the charges for the lithium fluoride? What do we get if we add up the charges for the sodium oxide? If you said that the charges add up to 0, you would be correct. Notice in the first example we have a 1 plus and a 1 minus. So that's like taking a positive 1 plus a negative 1. That would equal 0. In the second example we have two 1 pluses and a 2 minus. So this would be like taking 1 plus 1 plus a negative 2. That would also equal 0. This is not a coincidence. The net charge on any ionic compound is always 0. And notice that's in bold here, so it's probably kind of important. So we'll say that again. The net charge, or the total charge, on any ionic compound is always 0. This happens because whatever electrons are lost are also gained. So if we have 7 electrons that are transferred, that would give us a total of 7 minus charges and 7 positive charges, which would always add to 0. So we could write some formulas for these compounds. For the lithium fluoride, it would be LiF, because there's one ion of each, one lithium ion, one fluoride ion. For the sodium oxide, it would be Na2O. And notice the subscript 2 here is used to indicate that we have 2 sodium ions. So we've been able to describe how an ionic bond forms. Now we want to be able to write formulas for ionic compounds, combining what we just saw with our knowledge of the ionic bond formation with what we now know about how those charges of the ions will always compare. There are a few rules we want to be familiar with for writing formulas. You've actually just seen them in the last examples here. We always write the cation symbol first, followed by the anion. Recall the cation is the positively charged ion. The anion is negative. Whenever we write the formulas for the compounds, the charges on the ions do not appear in the formulas. We use subscripts to indicate the number of ions other than 1. If there's just one ion present of that particular ion, we do not include a subscript. It's understood to be 1. And an important thing to remember, the net charge on the compound must equal 0. That's how you will determine how many of each ion you need in order to balance the formula. So let's look at some examples. We want to write the formula for each compound. First one, we have magnesium oxide. Let's take a look at the name of this compound before we try to write its symbol. Notice we have 2 words here, magnesium and oxide. What this tells us is this compound is composed of 2 ions, a magnesium ion and an oxide ion, or I should say 2 different ions. There might be more than one of those ions. That is possible. Notice for the metal, or the cation, the name of the metal is simply given. It's just the magnesium ion. And then, as we know, for the anion, we use the IDE ending. So it would not be magnesium oxygen. We use the IDE ending for those monatomic anions. What you want to do before you try to write the formula for the compound is find the charges on each of those ions. So we can look this up in the periodic table. We know magnesium is in group 2, so it'll have a 2 plus charge. The oxygen, which forms the oxide ion, is in group 16, so it'd be 2 minus. So consider these charges here in these ions and ask yourself, how many of each ion do I need in order for the charges to add up to 0? Well, if you look at the charges here, they're going to balance or cancel each other if there's one of each, because I have a 2 plus and a 2 minus. So the formula for magnesium oxide is simply MgO, because if I have one magnesium ion, it will cancel with the 2 minus of the single oxide ion. So thus the formula is MgO. Let's take a look at another example. Calcium fluoride. Again, find the charges on the ions before you try to write the formula. Calcium is 2 plus because it's in group 2. Fluoride is 1 minus because it's in group 17. Now consider how this compares to the last example. In the last example, the charges on the ions would cancel each other because they are of equal magnitude, 2 plus and 2 minus. Here that is not the case. We have a 2 plus on the calcium and only a 1 minus on the fluoride. So ask yourself, how many of each ion would we need in order for the charges to cancel or add to zero? Well, if you said you would need 2 fluoride ions, you would be correct. If I had 2 fluoride ions, that would give us a total charge of 2 minus. That would cancel or balance with the calcium's 2 plus. So the formula is CaF2. Couple more examples here. Rubidium nitride. As always, find the charges on the ions first. Rubidium is 1 plus, nitride is 3 minus. Now ask yourself, how many of each ion do we need in order to balance the equation, or I should say balance the charges on the ions? If you said you would need 3 rubidiums and 1 nitride ion, you would be correct. If we have 3 rubidium ions, this would be 3 1 plus charges for a total of 3 plus. That would cancel with the nitride's 3 minus. So Rb3N is the formula. Last example, we have aluminum sulfide. Aluminum is 3 plus, sulfide is 2 minus. This one is a little more complex than the previous examples. Ask yourself how many of each ion you would need in order to cancel the charges. The problem you might run into on this situation is if you add a sulfide ion, then you get to more than 3 plus. Actually, if I had a second sulfide ion, that would get me to 4 minus. So actually what's going to happen here is you're going to need multiple of each ion. Probably the best way to think about this is to think, what is the least common multiple of the numbers 3 and 2? In other words, what is the smallest number that both of those numbers divide into evenly? And the answer to that is 6. 2 and 3 both divide into the number 6 evenly. So ask yourself, how many aluminum ions would we need in order to get a total charge of 6 plus? Well, the answer to that is 2. If I had 2 aluminum ions, I would have a 3 plus and another 3 plus. That would give us a total of 6 plus. For the sulfide, I would need 3 of them. I would have a 2 minus, a second 2 minus, and a third 2 minus. So 2 minus plus 2 minus plus 2 minus, that's 6 minus. So the answer, the formula, is Al2S3. Here are a couple of practice questions or practice problems. I would take a look at the question, pause the video, try to answer it yourself, and then proceed to see what the correct solution is. First question, explain how an ionic bond forms. I suppose you've had a go at it. Many ways you could answer this, but a basic answer would be something along the lines of this. Ionic bonds form as the result of valence electron transfer between atoms. The transfer causes both a cation and an anion to be formed. These oppositely charged ions will be attracted to each other, thus forming an ionic bond. The whole idea there is we get oppositely charged ions due to electron transfer, and then those ions are stuck together because of their opposite charges. Second practice problem. Write a formula, or the formula, of each ionic compound. So you're given 3 here. Go ahead and pause the video, try to write the formulas for each of them, and see if you can do it correctly. Here are the answers. Lithium oxide is Li2O. I get this because lithium is 1 plus and the oxide is 2 minus, so I would need 2 lithiums for every oxide. Strontium chloride. Strontium is 2 plus. The chloride ion is 1 minus, so I need 2 chloride ions for every strontium. And then calcium phosphide. Calcium is 2 plus. The phosphide ion is 3 minus. So I would need 3 calcium ions for every 2 phosphide ions to give us a net charge of 0. This completes the second lesson in our chemical bonding unit. We've been able to describe how an ionic bond forms and draw diagrams to show this. And then we've also been able to write formulas for ionic compounds.